Well, hello friends. So in this video I will be discussing regarding positive operator valued measure, which are also called as POVM measurements. So you see, again, as per the measurement postulate, it says that you give me a set of measurement operators and what are the corresponding these are just indices, but eigen values, if you say, or the outcomes, if you say, such that I have not written an important thing, that is, these operators should always satisfy this completeness relation. This is necessary. So then the final state, if outcome M is obtained, the final state is rho final, that is I have shown here, and your probability is just a trace of this, that is a condition of normalization. So with this much, what is POVM? So you see, if in most of the measurement, if I don't want the final state, I don't want to know what this final state is, I just want to determine the probability. So mostly in case of statistical experiments, you can directly use this definition to write PM equal to, by cyclicity of trace, mm dagger mm rho. That's just cyclicity of trace. Now let's write it as EM rho. So this probabilities, if I am only interested in the probabilities of getting these measurement outcomes, then this operator, this EM operator, equally suffices me. If I know this, I know everything, such that this condition just reduces to summation over I. This should be M. Summation over I EI equal to identity. Okay. So what is the point of POVM is, POVM says, give me a set of EI operators, and these are the outcomes they produce, such that they obey this completeness relation. If you give me this much information, I can with certainty predict all the probabilities. So why is POVM useful? We will understand it using an example. Let's consider one state, that is this, and let's consider one more state, that is this. You see, if I have been given any one of these two states, and suppose I measure what is the probability of getting 0 using the operator 0 0. Using this operator, I find what is the probability of getting 0. Then after measurement, my state will always become 0. Okay, that's the collapse, if you wish. So in that case, but you see, you perform the measurement once. If you get final outcome 0, it doesn't mean that the initial state was this, because this state can also give the final outcome 0 with a probability half. So this is the thing, that you cannot distinguish these two quantum states completely. And that is quite obvious. That is just a manifestation of the superposition principle, and that is the reason why classical mechanics and quantum mechanics are so different. So this state and this state can't be distinguished completely, because this state has some component or some component of this state. But you see, with POVM you can do a pretty good job. Okay, so let's consider a POVM. The POVM will have elements like this. Okay, now I need let me see. I need a POVM that projects this one. So what I must do is so let's call this first operator in this POVM set as E1, the second operator as E2, and then third operator is I minus E1 minus E2. And obviously this choice automatically ensures this, and it can be verified that they forms a POVM. So now you see, now consider a black box. This black box has E1, E2, E3. In some arrangement, this black box has these measurement operators in its build, and out of these blocks there are 3 lights: light 1, light 2, light 3. Okay, now if you put in one of the state, someone gave you one of the state, so if you put in one of the state and suppose this light blinks, if this light blinks, what does that mean? That means the state that you have put in has some component of 1 1. But you see, this state doesn't have any 1 in it, so the state that has gone in must be this state. So you clearly distinguish between these two states. Now let's consider this guy. If this blinks, so this side drive is present. Okay, let's consider this guy. So if this blinks, that means you see if this blinks, so if you have a state, if this blinks, that means this operator has acted. But if you take 0, then that will be just 1. So if this blinks with surety, you can say that, well, hang on. Okay, I did a mistake. Well, so I wanted to choose the orthogonal states. Like you have 0, that's why I chose 1 here. You have this state. This is nothing but the state along x direction in the Bloch sphere. So that's why I choose this orthogonal state, which is orthogonal to this. Now if 2 blinks, then definitely this state can't be there, because this operator annihilates this state. So the only possibility is that psi 0 is present. Hence, you see, you can clearly distinguish the states by using a POVM, which you couldn't have done, for example, using a projector. So you see, so if one blinks, then this state is present. If 2 blinks, then this state is present. But the interesting point is if 3 blinks. If 3 blinks, then you get no information. So you if you see 3 blinking, then you have to just throw out your state and have to redo the experiment. So that is one of the cost that is there of this POVM. Okay, now that I have described projective measurements, POVMs, so let us look a bit at one more important concept. This is regarding entangled states. Okay, so you see before that, you have been given one Hilbert space. This is a two-dimensional Hilbert space. You have one more Hilbert space. This is one two-dimensional Hilbert space. Now you have to describe a system of the combination. Suppose you have access to a spin half particle, as well as you have access to a computational basis 0-1 particle. Then you have to describe both of the particle together, and at that moment the tensor product comes in. So this is really one of the postulate, the last one. So you see, so the tensor product. So let the state in this Hilbert space be alpha 0 plus beta 1. Let the state in this Hilbert space be gamma spin up plus delta spin down. Okay. Now the tensor product will be a good way to understand it is put it in column, tensor, put it in column. Okay. The final will be alpha gamma, alpha delta, beta gamma, beta delta. So this will be the final state. I hope you can see this. Such that what are the bases of this state is 0 up. So you have 0 up, you have 0 down, you have 1 up, you have 1 down. These are the bases, and even you can rewrite the bases as 0 0 0 1 1 0 1 1. You can rename the bases like this. So this is one of the concept of this tensor product space. Now this is a tensor product of two-dimensional. So it is a 4-dimensional Hilbert space. You can see there are 4 basis vectors. So that really justifies the fact that it is a 4-dimensional Hilbert space. There are several concepts that this 4-dimensional Hilbert space has 4 twos are 8 entries number. So it actually belongs to a sphere of S7. H tensor H space, it belongs to 7-dimensional sphere embedded in R8, and you can use quaternion representations to visualize this as the Hopf vibration to S4 with S3 as the Hopf fiber. You can see one of my previous videos. I have done this for 1 qubit state, but anyway, we won't go in those details. So I think that's all for today. I hope it was clear what is POVM and tensor product states. I will in next time discuss about entanglement, and I think I may also discuss regarding quantum teleportation. So well, thank you.